This is the Internet Court of Truth and Lies, and I'm going to be the plaintiff on this trial today. The reason for the truthcourt.net is if you've got something that you believe is true and you want to know whether other people believe is true, or you've got something that you believe is a lie and you want to hear other people dissect it as whether it's the truth or a lie, then this is a place to come. Today, I'm going to do a case out of physics. The case is all about photons, which are in physics essentially particles or wave-like particles that carry light, radio waves, X-rays, any electromagnetic energy. Everything that you experience in life, every object that you touch, how your brain works, everything that you can have an experience with in the universe without super special equipment is a product of either electromagnetics or gravity. Electromagnetics is where you get things like the fact that this paper, you can touch it and your fingers don't just go through the paper. Because if you look at the atoms in your hand are so spaced apart, and the atoms in the paper are so spaced apart that except for the electromagnetic or electrical and magnetic repulsion that's taking place, your fingers would go right through that piece of paper and the atoms would never touch each other because the atoms are so far apart. But the electromagnetics around the atoms are so strong that the atoms in your finger are actually repelling the atoms in the paper, and the atoms in the paper are repelling your finger. And all of that is electromagnetics. A photon was really discovered as a real thing by James Clerk Maxwell in the 1870s. And he had written about it by around 1850. But what he did was he wrote a book called The Treatise on Electricity and Magnetism, which has the same stature as Isaac Newton's work. So it defined the electromagnetics that we know today, the physics of it. And one of the things he did was he said, here is magnetism. So you take magnets and show them attracting and repulsing each other. And here is static electric charge, like when your hair goes frizzy, or you rub a rug and you get a little electric charge. And it turns out in his book, he did the equations that relate the electric field around something and the magnetic field around a magnet. And it turns out the equations are the same equations. And so in chapter 22 of his book, he said, these are exactly the same equations. And I'm looking at the equations for what at that time was called the luminous ether, which is light, visible light that you can see. And all of the equations were the same. And he said, I think light that you can see is just electromagnetic waves. And he then proceeded to tell you how light worked. It turns out that we know light today as photons in something called the Standard Model, which is a particle model. The idea is a particle is really that something has a specific direction and a specific target. So you can imagine a wave that starts from a specific place and it radiates out from that place. If it's got more intensity in one direction, the wave can go as a particle in the sense that if it doesn't have a certain energy level that wave hits, if it's too low energy, nothing will happen. But if there's enough energy, then the thing that it hits can potentially change. For example, if it hits an atom, the atom can respond by giving off an electron. That's what's called the photoelectric effect, and that's what Einstein got his Nobel Prize for, along with Planck, a guy named Ernst Planck. They jointly got the Nobel Prize in something like 1916 or something, on this idea that light can cause an electric charge. And the electric charge, if it radiates light or radio waves or X-rays or whatever, then it can not only carry the electric charge, it can be seen. The retina in your eyes have neurons that have photosensitive receptors. There's two general classes, rods and cones, that everybody's heard about. Those receptors respond to light with enough energy. And by the way, the minimum energy the light can have to be a particle to cause an electron to be affected in an atom or floating around among all the atoms. The minimum amount of energy is called the Planck's constant. That's the reason Planck got the Nobel Prize along with Einstein. A Planck constant, in terms of the size of the thing, in terms of the amount of energy, is something like 10 to the minus 33. That's in front of a 1. In other words, it's a very small number. So when you're seeing light, you're seeing trillions and trillions of photons impacting your retinas. And then the retinas, the sensors, the rods and cone neurons are responding because electrical is being generated in the molecules of the retina. Those are turning into electrical signals that are going through your nervous system in your brain to basically the visual cortex in your brain where you see. And all of this is happening via electromagnetics. But the original stuff that you see is coming in as photons. So one thing about photons and these waves that we're talking about is you can't actually see them. So the way you can usually illustrate this is if you have a laser and you look at in a room without dust in it, okay, just a room that doesn't have dust flying around the room. You can turn on the laser and you look at the light, you attempt to look at the laser light from the side. So the laser is going in this direction. You won't see anything because photons are completely invisible themselves. They are totally invisible. Nobody has ever actually seen a photon or one of these waves. What is one of these waves interacting with some external surface like a piece of paper and light on the paper, and it shows you the paper, and then that reflecting off as a photon into your eye through your glasses and cornea. The photon that you see, if you've got glasses, is not the photon that originated on the sheet of paper. The photon that you see is the photon that interacted with your glasses to refract a little bit. And that actually created a new photon, which then went into your eye. And when it went through your cornea, it actually created another photon, which exited your cornea into the back of your eye, which was yet another photon. And then it finally landed on something that absorbed the photon, and the response to that absorption was to stimulate a neuron in your eye. And then the neuron in your eye reports it out as a hit. I have reacted to a photon. But you've never actually seen the photon. In fact, I just totally didn't see the photon that came to your glasses. The way a photon is refracted, that was proven by a theorem about 20 years, 30 years after Maxwell. And it's called the OSEEN. There's another name there, OS theorem. And what he showed was that when you have refracted light in water, you'll read about that. The people will try to explain that to you, and they'll say the wave in the water has slowed down. The light wave has slowed down. That's a lie. That is not true. What happens is, and this is proved by a theorem, photons always go exactly at one speed and one speed only. That's light speed, which is about 300,000 kilometers per second, or 300 million meters per second. Photons are very fast. They can go around the globe. If you could get a photon to curve around the globe, which you can't, but if you could get one to curve around the globe of the Earth, then that one photon would go around the Earth many times before the first second goes by. So photons are incredibly fast, but we can measure their speed in a vacuum. Even when a photon is going through the glasses here, the photon hits the surface, interacts with some of the molecules in the surface of the glass, gets absorbed by the atoms, and then the atoms will re-emit the photons in all directions. Some of the light will reflect back from the front of the glasses, and some will generate new photons inside the glasses. The way that interacts with each other is that the wave fronts then interact with each other and actually create bands of interacting light. The way those bands are established by this theorem is they will cancel the direct ray of light through the glasses and create a new wave of photons being passed, but now interacting with each other in such a way that a false wave that does go slower than light will be created that will carry the light through the glasses until it exits the other side, and then it will refract out into the space and reconstitute light. This is proven. But the big key behind this is that the photons never die. They don't know time. They literally don't know time. So when you look up in the night sky and you see a star or a galaxy, if you see a star, it could be 50,000 light years away. That photon that traveled from that star to your eye is the same photon, and it traveled at light speed. A light year is about 10 trillion kilometers. That's what a light year is. It's traveled for 50,000 light years and never been anything but that one photon. You take the view of being a photon and traveling through space, what the lifespan of a photon sounds something like this. All of a sudden, it comes out of an atom or electron or some other part of an atom, like you can get them in splitting protons and neutrons and stuff. The next thing it knows, even if it's 50,000 light years later, is it hits something else like the surface of my glasses, and it gets absorbed into an electron or some other piece of an atom. and that's the end of that photon. This is crazy. They're incredibly small amounts of energy. There's this 10 to the minus 33 amount of energy, but they live forever. And it's very possible for photons to have been traveling since the beginning of the universe. And that's what the James Webb telescope is seeing when it's looking at the very deep space that goes back 13 or whatever it is billion years. Those photons have been traveling just through the vacuum of space, not interacting with anything from those original sources since the beginning of the universe. And those photons were born 13.4 whatever billion years ago. They didn't notice any time. Time is really not defined for them, but massy objects, things that have mass, are defined for it, which is it can be generated from something with mass, and it can be absorbed or be absorbed by something with mass. And that's the entire life of a photon. Photons always go in a straight line. The direction the waveform is set off in is the direction it will stay in forever until it hit mass, like glasses, and it can get refracted. But what's really happened is the glasses have absorbed and made that photon go away, and then the glasses generate new photons that go through the glasses, and they interact in such a way that it looks like the light has refracted, and then they come out the other side and refract out again, because they're outside of that medium that's creating the fake waves. And then when they're out in airspace, which is essentially vacuum as far as photon is concerned, the likelihood of a photon hitting anything in the air around you is very small because the air is so undense in terms of atoms. It is electromagnetic. And so one of the properties of the electromagnetic waves, Maxwell's original thing, is light has a wave that goes like this, which is the electric wave, and then it has a wave that goes like this, which is the magnetic wave, and they're always at right angles to each other. And the direction of the electric is what's called the polarity of the light. So when you're looking through polarizing dark glasses, for example, the light that's getting through the dark glasses is polarized has the same polarization as the glasses select, and that's the direction of the polarization. So light has this characteristic that can be polarized. And so think of whenever you're talking about photons, you're talking about gazillions of photons in a light beam. An average little laser pointer, when you put a little dot on the wall with a little red laser pointer, you're putting about 13 quadrillion photons on the wall that are interacting with atoms on the wall. A lot of the other atoms, so there are some atoms that never made it, that never got reflected, but over 13 trillion photons did get reflected off the wall for the laser pointer. Quadrillion. So when you're seeing light, you're seeing these huge numbers, but each little photon is each little photon, and each little photon has its own little lifespan, and the lifespan has no limit. The only thing that can alter the direction of a photon and it still stay a photon is gravity, which is general relativity. So you can have a photon being curved, but it thinks it's always going in a straight line. It's space that's curved. That's Einstein's general relativity. But from the photon's point of view, it's a happy little photon thinking it's going in a straight line and never notices that space is curved. So that's the story behind photons. They don't know space. They have a beginning and an end. And as far as photons are concerned, there's no time lag between when a photon is emitted by a piece of mass 13.4 billion light years away and the time when it strikes our glasses. It's just mass to mass. And so the mass of the two ends, as far as the photon is concerned, is where it just went because it took no time to get there as far as the photon was concerned. It just took no time, even though to us it took 13.4 billion light years to get there. And they don't know gravity because they think they're just going in a straight line. Gravity can bend light, and it is the same photons that it's bending. It's not, unlike refraction in glasses and stuff like that, the photon is not absorbed. The photon is just being bent by gravity. So photons don't know space, time, or gravity. And that's the argument. And by the way, what I'm saying here is largely accepted in physics, which is crazy. These people know this stuff and they don't explain it to other people. So I'm going to say, is it the truth? This is crazy sounding, but it's the truth. Photons are eternal as far as we know. Actually, the math says that photons are, when they're born, they're basically eternal until they hit some mass. And when they hit it, by that it means that they get close enough to do electromagnetic interaction with the mass that can cause the photon to die. And the electromagnetics in the mass change, which is what your eye sees, and so forth and so on. So they're eternal otherwise. So if the photons never hit anything and go on forever, that's not a problem. Is it the whole truth? I think I said it. So there is another little facet of it, which is that even though it's still a photon, if it hits a mass, part of its interaction with the mass can cause the mass to be pushed. And that's what you see when you see light sails in science fiction. But light has the ability to push things. Photons have the ability to push things, but they're really not doing anything. When the light enters your eyes and goes to your retinas, when it interacts with the molecules in your retina, it's pushing it. But the amount of push is very small. It's the spectrum of this Planck constant thing. And so you can't feel it, but you can set up situations where you can see light exerting pressure and moving mass. This is what the accepted math that, quote, explains reality in physics says. There's no deceit. And I've had this article out and I've yet to have a physicist object to it. The motivation here was to be informative, to tell people what a photon is. And we only know it well by the analogy, which is in mathematics. So in math, we can give you an analogy of what a photon is. Since you can't see them, you can't feel them, you can't do any of that stuff, what you're feeling is a photon interacting with something that you can feel, atoms. But the photons themselves, you can't sense unless you're struck by one. And then you only sense the result of being struck by one. You don't sense the photon at all. They're too small to sense. What's the social acceptability of the truth or lie? The amount of modern civilization that came out of Maxwell's understanding is basically most everything today is understood in terms of electromagnetics around atoms. A lot of these things that you may hear about can be real, but they're not. So, for example, there are other particles. There's things like neutrinos and so forth that are not photons. I'll show you. This is light speed, the velocity. This is 300,000 kilometers per second. And this is relativity. So if you look at the beginning of this, up to over 250,000 meters per second. The distortions that you hear about in relativity are not there. They're there in very small amounts, but you really have to get really close to light speed before things start getting really distorted. One of the properties of going faster and faster relative to light is that nothing can go faster than light. Light only goes at light speed. You will hear that it doesn't. That's not the truth. The truth is that the photons are always going light speed. That's the only speed they go at. What you're seeing is the Ehm theorem going off. They can appear to go slower because the wavefront is canceled in a certain direction and a new wavefront is generated in another direction. That wavefront is also photons, other photons, new photons going in this sort of other direction. It can come back out and go back in the same direction again. And again, it's coming out of that surface where you have these derived waves going. So this was the front page of a magazine article I wrote in the 80s. And this was a rectilinear grid. It was a grid that was a square of pipes and dots, essentially, that was perfectly square, flat, the way you're looking at. So the rectangle was like this. And then going near light speed, and this is 0.999 light speed. When you get to the front and you increase the speed up to light speed, the grid will rotate 90 degrees and will turn into a sphere. And then when you go through the grid, and this is actually inside the grid a little bit, some of this edge around here is actually in the past. So this is the traveling as a photon through that grid, and what the photon is seeing, what it can measure, if it could measure anything, this is a thought experiment, is it can see the past in front of it, and it can see the entire universe. So if you did a thing of all the stars in the universe, from the photon's point of view, all the stars in the universe collapses into a very small circle in front of the photon. And it either hits something or doesn't hit something. And by doesn't hit something, it means it hasn't hit something yet. It may never hit anything, but in this particular case, when we simulated this photon, that's the other end of the rectangular grid right in the middle there. And this photon will go right through that grid and come out the other side and never touch anything in that grid. But this gives you what it would see when it goes warp speed, what it would see if it could be human. But of course it can't. But it gives you an idea of how, and these distortions are real. So the distortions you're seeing are anything that could be measured when you're going at the speed at 0.99, the speed of light. This is your reality. The entire universe can collapse. We actually did a video that was done in Japan that was shown Japanese TV, where we did the physics to show the entire universe coming when you go to warp speed, when you go to light speed, which no one can get to light speed. Nothing else can get to light speed because it will go to infinite mass when it hits light speed, which is not possible. But it will go to light speed, and then when it goes faster than light speed, you watch the universe explode in front of you, which is oddly exactly what Star Trek was showing. And they must have had some physicist explain to them the same math that we worked out and said, this is what going through light speed would look like. And so what the movies show going through light speed would look like, if it could ever be done, is approximately correct. So I'm going to do the jurors now. Juror 1. This is a 20-minute summary. Yeah.
Or, yeah, I'm juror one. Robert, I don't know. I have to say, I've come down pretty hard on plaintiffs who just use encyclopedic.
That's funny, Andrew. You're silly.
Yeah, I'm sorry. This has been a thing for me. I was one of the top physics students at Emory when I went to college. And the reason I went into psychology was I decided that the physicists couldn't actually understand reality unless they understood how the human brain computes. The physics got into me and it never left. And I apologize profusely.
We can tell you really enjoy it, Bob.
Yeah, it's just, totally crazy stuff.
I don't know, irrelevant in some way.
Except it's not. It's running your life right now. You just don't.
Yeah, I'm quite interested in this, but I don't think it makes a case, a trial.
Okay.
That's my feeling.
I'm just declaring that the photon's perspective on the world is that it doesn't know time. It doesn't know space. It just knows adjacency. It just knows that it came from something. All of a sudden it came from something. And from the photon's point of view, the next thing it knows is it hits something and it dies. So there's no time. From the photon's perspective, the difference between a second, an hour, and 13.4 light years is the same amount of time. It's crazy. And the gravity, it doesn't know it because the photon is always going from its perspective in a straight line, even though space-time is curved, because it doesn't know space or time, doesn't know gravity. So that's my one argument.
Does it know space and time in the Hadron Collider, the CERN Collider?
So
they make
photons cannot be accelerated.
Isn't that what they do at the CERN Collider?
No, they do not. So you can only accelerate something with mass, and a photon has zero mass. So it's accelerating different kinds of particles, but usually electrons. They can accelerate an electron to near light speed, but not light speed.
We have the CERN Collider here in Chicago, and I was looking that up, and it spoke about them using protons.
No, protons. That's not photons.
Oh, Jesus, I'm sorry. Yeah.
A proton is about 1,000 times more massive than an electron. And it's got the positive charge, and the electron has the same charge, but a negative version of the same charge. And yet the electron is 1,000 times lighter than a proton. An electron, a proton can be accelerated. So you can get an electron up pretty close up here to the top, but a proton bringing it up to that speed requires things like that collider, and we're still way down here with a proton because it started with 1,000 times the mass that an electron started with. And if an electron, which is a very light particle in terms of mass, gets up into these speeds, an electron can kill you. So that's the reason you can't stand in front of the collider in Chicago. So juror 2, sorry.
That's me. I concur with you, Bob. It's still as clear as mud to me, but I learned a little bit, and I kept thinking you were saying Botox. But I know you're not, but I can see why you thought it was proton instead of photon. It's wow.
Yeah.
But thank you. It was a good case and challenging, because how can we challenge about something we don't know?
Yeah, so I actually understand that. And the reason I brought the case was, honestly, I wish that some of these science communicators would bring cases, the science communicators on the web, to find out whether or not they're explaining things well enough for people to understand what they're saying.
No, that's a good idea.
Yeah. And they should be bringing cases and then getting people's responses to what they say to see if what they're saying makes sense to people.
But how does that differ from just a lecture?
So the difference in that, what y'all are telling me is, so Robin just said that she understood a lot of this, and so she actually tended to agree with me. But several of y'all have said I don't have a clue. I'm simply saying what I'm telling you I believe is completely true. The truth has some unbelievable properties to understand what a photon is and what light is and so forth. And, by the way, the same math for visible light works with X-rays and radio waves. That's all the same photons. They just have different energy levels.
So the photon would have something to do with the atomic bomb. Is that?
Oh, yeah. So in the way that the atomic bomb explodes is that first bright flash, those are photons.
Gamma rays.
Gamma rays are just very high energy photons. And that first flash is incredibly destructive because photons can push and they can get absorbed. And those high energy absorptions can pretty much destroy you. They can burn you terribly. The photon just got born at the beginning of that bomb, died the second it hit you. That initial part of the blast is a photonic blast. And then it follows with the 2 or 3 other types of blasts. But the first one is the photon blast, which is why they say never look into an atomic bomb going off. Don't do that. That's a very bad idea. Okay. In fact, cover yourself or you'll just show up as a shadow on a wall. So are we at juror 3?
Yeah, that's me, Bob. Yeah, this was way over my head, but I have more questions than anything else. Is time travel even possible? And a simple analogy, a black t-shirt, what happens to the photon if I'm looking at something black?
So a photon, a black t-shirt. What do you mean?
Yeah, or a black wall. There's no light emitted
Oh,
from
no,
what
yeah.
happens to
If you
a black
if you put
hole. Yeah.
a light on a black wall, some of that light will almost certainly reflect off the black wall. This Owing theorem tells how light reflects as well as how it refracts. And there's no such thing as a real black wall. There's something called a black body, which is technically a sphere. The interior is painted black, and the photon goes into the sphere, bounces, or any reflection it has. So little of it can ever get out of the front that the sphere will just be the blackest of blacks.
Mm.
There are paints that are very black, but there's no such thing as a black t-shirt. It just looks black to you, but you can see the t-shirt, which basically means it's not perfectly black. It doesn't just make the photons go away. And you know,
So the fact that I can see something means there's a photon that affected that thing.
you can see something is a photon that hits your cornea, generated a photon out of your cornea to a nerve cell there was a rod or a cone sensor that had some molecules in it that reacted to that photon by absorbing the photon. And then that caused the nerve to start chirping away to other nerves through photons, by the way. So this is really photons talking from one molecule to another. It's crazy. So when you see the smallest dot of light you can possibly see in your brain, you're probably generating trillions and trillions of photons inside your brain.
Okay. Mind-boggling.
On very short distances, but they don't know distance.
Sure. So I guess time travel is not possible then.
No,
Right?
you can go slower than time. So what relativity says is that you can go. So if you're traveling along at one speed, something that's traveling faster than you, a lot faster than you, can be going at a slower rate of time to you. Okay. And so it will age slower. But there's no such thing as something that that is going to be going faster than you, except from if you turn that around, so the thing that's going slower than you, now it's looking at you and it's thinking that you're going fast. So what was you is now going slower in time to it. That's relativity. And those are real effects. So you age more slowly, but you really have to be going very fast before you can detect that. So that's the reason when an astronaut goes up into space and circles the globe at 17,000 miles per hour and circles around, he lands and they say the astronaut is now 10 seconds younger than you are.
Okay.
But it took a long time for him to get there because nothing in the universe is really going that fast with respect to anything else, unless they're incredibly small particles like electrons. They can go near light speed. But when they say electrons go near light speed, it's about 2% of light speed. It's crazy. The physicists are lying again. They're saying this is going near light speed. What they really mean is it's going really fast, but nothing like what light speed is. So there's nothing in the universe that you can see from Earth that is going very fast. You can see things that are going 300 kilometers per second. That's typically a very fast thing that's happening out in the universe with respect to you. And remember, light speed is 300,000 kilometers per second.
Okay.
So the stuff out in the universe is going very slow compared to light speed. That's one of these crazy things that the physicists don't tell you, is they don't tell you that things with any real mass to them just can't go very fast because you can't give them enough energy to go fast. And the energies needed to move them very fast are just such huge energies. And if they do go very fast, they can age much slower than you. But and distances can get, I don't want to go into that. We're going to run out of time. So juror 4.
I was going to say, I put a couple notes down, what Bob said, period. And the other note, the only thing that stuck to me is they do not carry a charge, they carry force. So when you're talking about them snaps and stuff.
Well, so they carry both electrical and magnetic energy. It's not necessarily enough energy to cause an electron to move. And it's the electron that carries charge that you can feel. That it takes a lot of electrons to be electricity to you.
Okay.
But a light wave is electromagnetic waves, and they are electromagnetic. So you can interact with light waves electromagnetically. So when they get absorbed, those are electromagnetic interactions. That's the photoelectric effect. A light hits a surface and it gives off an electron.
Thank you. I'll be very brief because you're only halfway through.
Yeah, I know. Okay, so juror 5.
That's me. I'm completely lost, Bob. I'm not even gonna lie. I'm lost. And I just agreed with you because I pretty much knew that you knew what she was talking about. So
I sound
I'm
like I
lost.
do. Yeah. So if they think that I lied.
That's me. I could have sworn that as of visiting the lab a handful of times, that the photon had something to do with the God particle or their search for dark matter.
So not the photon,
CERN
but the
collider.
neutrino. The neutrino does. The neutrino has mass.
Yeah.
And it travels so fast.
Yes and no.
Yeah, so neutrinos do not interact electromagnetically with other things.
Talking about photons? No, this subject is on photons, correct?
Yeah, photons.
Photons are the fundamental particles of light, and they're
Yes.
used to, yeah, so that has something to do with the Fermilab search for the God particle.
Right. So if a photon hits something, it can get reflected or it can be diverted. It can cause that something to change its state, like an electron can get created, for example, from a photon hitting an atom. There are various things But what they're doing is they can only accelerate particles with mass. Photons have only one speed. They can only go straight, except for the fact that gravity is space itself. But from the photon's point of view, it's only going straight. And so the Fermi lab cannot accelerate photons, but they can accelerate any kind of particle, which can then hit another particle, and photons can be given off when two particles or one particle hits another particle. And you can give off photons and other particles. And that's what they look at Fermi Lab and stuff like that. So yeah, they're right that photons and something called the Feynman diagrams. I don't know if you ever heard of those. These are these little squiggly diagrams. The Feynman diagrams were originally created by Feynman to just be photons and electrons, and what happens when electrons hit other electrons and so forth and so on. And it shows what a photon is doing, but there's no way that the photon can be detected except because it hits something.
Don't they have something at Fermilab that detects single photons?
Sure, that's the photons. It's the same as the
single photon detector.
What they're doing is they are decreasing the amount of energy that's put into the light. They decrease it till the amount of energy gets close to the Planck energy. If the photon can be detected, it's got to at least have the Planck energy. So if you detect something and you detect it has 2 times the Planck energy, that's 10 to the minus 33, then you say you've got a single photon detector, because you can't detect a wave that's less than that amount of energy. So if you have a detector that can detect the amount of energy associated with one photon, which is the Planck energy, then you can say that you are detecting single photons. And if you've got something that can produce just that small amount of energy, you can say I'm generating single photons. Although in practice, they're really not. They're generating them in the hundreds or thousands, but not in the quadrillions.
I'm going to clip this and tag Fermilab on Twitter or X, and we'll see what happens.
Absolutely. See what they say. Juror 7.
Hi there, Bob.
Hey.
I said photons do get affected by gravity, just not in the way we usually think. For example, their paths, they bend near big planets or stars. So saying photons aren't affected by gravity at all is like saying sharks don't
Oh
get
no, that's not what I said. What I said was that photons don't know the gravity. They think they're going straight.
Yeah, that's why I'm saying, like, I made a comparison. I said saying photons aren't affected by gravity at all is like saying sharks don't get cancer. It's
affected by gravity because gravity changes what a straight line means in the world, but it's not the photon that's changing it. It's the space-time that's changing it.
Yeah, that's what I said in the verdicts, because they are affected by gravity. It's just because they're massless. So
Yeah.
it's a bit harder to detect when it comes to photons. So yeah.
Yeah, photons, I actually regard photons as one of the most interesting things on the face of the planet. I think you can understand most all reality by just understanding photons and electrons. The nucleus of an atom is a way of keeping the electrons in check. Because without the nucleuses of atoms, or without the protons, the electrons would be roaming free, and we would all be burned up really fast. Because the electrons have mass, and when they hit you, burning is electricity. And photons have pressure, but it takes a nuclear blast type pressure to burn you with photons. It takes a lot of photons. Juror 8. Did I run Juror 8 off? I'm sorry?
Juror 8's here. She's back in.
Sorry, you guys cut off for a while. But my notes on this, I don't know. I was very confused, but I did end up making little notes what I understood from the thing. It was while photons do not experience time or space in the way that massive objects do, they are still subjects to the effects of gravity, illustrating the profound nature of the universe.
So I promised at the beginning of this that I'd tell you all what green light was and red light. Green lasers is a scary thing to most physicists. The reason is that while a green laser and a red laser may have the same energy, they may both be half-watt lasers. Your retina, the neurons in your retina, are more sensitive to green light. A green laser and a red laser, the green laser will appear to be much brighter than a red laser. And most physicists I know don't want children playing with green lasers because we really don't know whether the green laser can do damage to your eye. It won't do the wattage type damage, but the eye is more sensitive to green. And it just is. It's just more sensitive to green, okay, which is a problem. And so that's the reason. But you can prove it to yourself. You get a green laser that's a half watt and a red laser that's half watt, and the green one will appear much brighter. And that's your eyes, not the laser. That's the receptors in your eyes.
Interesting.
Yeah, that's why Brian said the right thing. That's why night vision is green. Yep.
Yeah.
That's
I always
exactly
wondered that.
well, it's intended to be because your eyes are much more sensitive to green.
And I like the color green.
Green is great color.
Ah, but which green?
Which green?
Green
Any
is for the
green.
money, gold is for the honey.
Green, green, right? Yeah, which green? Yeah, that was pretty interesting, Bob. Even though I'm still lost, I'll be looking at photons and atoms and everything else probably for a week now.
Yeah. This has been very interesting for me because it's hard for somebody like me to know what makes sense to other people because this is a hobby for me. Okay. And I do math. So math does not bother me. I don't have a problem with math. I do require that the mathematician explain himself to tell me what he did. I get really mad when they can't explain themselves. And I say, when you can explain yourself and then tell me what you did and explain what this equation is doing and how it works, I will listen to explain it to me in a way that I can understand. I don't have problems understanding math because I will typically go and shake a mathematician until he starts talking. We'll see y'all, and I'm sorry I went over an hour, but I just had to take this one off. This has been a one that I really wanted to do.
It was interesting. Have a good week.
So we'll see y'all next week.